Welcome back to the deep dive. Today we're tackling something, well, frankly, a bit of a nightmare for anyone running modern digital services.
Oh, yeah. What's that?
It's about running complex applications, these lightweight microservices across environments that are just wildly different.
Ah, you mean from the massive cloud data centers all the way down to tiny sensors out at the far edge?
Exactly, that whole spectrum.
The Cloud Edge IoT Continuum,
Yeah,
or CEI.
yeah,
It's huge, it's messy, it's heterogeneous, and it's always changing.
right. And trying to manually manage an application that needs to maybe jump from a server in one country to a private device in another, it just sounds impossible.
It pretty much is, or at least incredibly painful. Which brings us to our source for this deep dive, the Codeco Federated Operation and Toolkit, deliverable D13.
Okay, Kudiko. Sounds promising. They're positioning this as maybe the next generation of orchestration, right?
That's the ambition. Yeah.
So let's break it down for everyone listening. What does federated operation actually mean here? And how is Kudiko trying to, well, change the game compared to how we normally manage these big, sprawling systems?
Right. So federated operation, think of it as getting lots of separate computing environments, different clouds, edge clusters, maybe groups of IoT devices to act like one single smart system.
Okay.
It's like managing a global fleet of self-driving cars. Each region has its own rules, its own resources, but there's some kind of shared intelligence coordinating it all.
That's a helpful way to picture it. And the key mission, as I understand it, isn't just managing the servers and the network gear anymore.
No, exactly.
It's about managing the application itself, wherever it runs.
Precisely. That shift is really crucial. Instead of the developer tearing their hair out, worrying where their code needs to run for performance or compliance, the platform takes on that burden. The system itself becomes responsible for making sure the application hits its targets, like how resilient it needs to be, how green, what speed it needs, no matter where its different pieces end up running.
And hitting those targets across that whole diverse continuum, that's the hard part, right? Because applications today, they need to be mobile, they deal with tons of data, sometimes needs super low latency, and they often need to be near a specific data source, not just the nearest CPU.
Exactly. And that specific need, that's what drives Codeco's core innovation, what they call Integrated Data Compute Network Orchestration, or DCN.
DCN. Okay.
And this is where it really differs from, say, standard Kubernetes, which mostly just focuses on the compute part.
Right. So let's unpack that DCN idea. If I'm the Codeco orchestrator deciding where to place a microservice, what are these three perspectives I'm juggling?
Okay, first you've got the computational perspective. That's the familiar stuff.
Yeah.
Processing power, memory available on a node, basic resources.
Standard stuff. Okay.
But then, crucially, you add the other two. Second is the data observability perspective. This is huge.
How so?
It asks, does this node actually have access to the specific data this microservice needs? Is that data recent enough? Is it fresh? And maybe even more importantly, does putting the service here with this data comply with regulations like GDPR for this physical location?
Ah, okay. So it connects the data rules directly to the placement decision.
Yes. It bridges the data workflow world and the compute world. And the third piece, the networking perspective, kind of ties it all together.
Makes sense. What does that look at?
It looks at both the physical network, the underlay, and the virtual network, the overlay needed to connect these containerized bits. It measures bandwidth, latency, packet loss.
Right, the usual network metrics.
But also, and this is quite innovative, it measures link energy consumption. You can't really make a smart placement in this edge cloud world if you don't know the true cost, including the energy cost of moving data around.
Okay, that really does sound holistic. It's not just about finding capacity, it's optimizing for cost, compliance, energy, the whole picture.
Exactly.
And just to clarify, this Codeco framework, it's built for containerized applications, right? And it can work with Kubernetes.
Yeah, it's designed to manage containerized application components like microservices. It's independent, but it's pluggable into Kubernetes, or K8s. So it can manage these components across multiple different K8s clusters.
Managing across multiple clusters, that's the federated part. How does it technically handle that?
So under the hood, it relies on Open Cluster Management, OCM. That provides the basic structure.
Which is that hub and spoke model.
Right. You have a central hub cluster that kind of directs traffic, and then multiple managed clusters, or MCs, out of the edges or in different clouds that the hub manages.
Okay, but now think about scale. If you have, I don't know, thousands of these managed clusters, factories, remote sites, whatever, searching all of them every time you need to place one little microservice seems like it would just break everything. Too slow, too much data.
Absolutely. That search space is enormous. And that's where they introduce a really clever concept called the neighborhood.
A neighborhood. Okay, what is that exactly?
It's what they call a semantic abstraction. Basically, it's a logical grouping, a predefined set of managed clusters. When you deploy an application, you map it to a specific neighborhood.
Uh-huh. So instead of searching the whole world,
Right.
the system only looks for resources within that defined, relevant area.
Exactly. It partitions the problem. It dramatically cuts down the bandwidth needed, the processing time, the whole search effort. It makes federation feasible at scale.
That's smart. Are there rules? Like, can a cluster be in multiple neighborhoods?
Yes, an application maps to just one neighborhood at a time. But a single managed cluster can definitely belong to several different neighborhoods. Adds flexibility.
Okay. And architecturally, where do the different Codeco pieces live in this hub-and-spoke setup?
Generally, the main brains, the decision-making parts, live on the central hub cluster. Things like the configuration manager, the central scheduler part, the metadata manager, the network controller.
Right.
And then out on the managed clusters, you have the agents doing the local work, collecting data, executing placement decisions, handling the distributed learning aspects we'll get into.
Got it. That structure makes sense. So now we know the context. Let's dive into the toolkit itself. What are the 5 key components doing the work here? Starting, I guess, with the entry point.
Yeah, let's start with Automated Configuration Management, or ACM. This is really the front door. It's the user interface. It handles deploying Codeco itself, and it manages the whole life cycle of the applications running on top.
And I saw something about a specific way developers define their applications for this, the CAM.
Yes, the Codeco application model, or CAM. That's super important. It's like the contract between the developer and the platform.
The contract.
Yeah. In the CAM, the developer doesn't just deploy code. They specify the performance they need. They use these profiles, like how much greenness or energy efficiency they want, the level of resilience, specific QoS needs like latency, even a required security class.
And ACM monitors if the app is actually meeting those demands.
Exactly. It collects status based on monitoring, compares it to the CAM, and reports back. It closes that loop.
Okay, component 1, ACM handles configuration and the CAM contract. What's next? You mentioned data observability.
Right. That brings us to the metadata manager, or MDM. If we're going beyond just simple CPU checks like we discussed, we need context, lots of it.
And MDM provides that.
Yes. It's the system's eyes and ears for data context. It constantly gathers metadata, things like data compliance status, how fresh data is, rules about where data can move, its portability.
Okay.
It links all this information together, enriches it, and builds this powerful knowledge graph. It uses things like Apache Kafka, event queues, to keep this graph constantly updated in near real time.
So it's like the bridge between abstract data rules and the actual K8's infrastructure.
Precisely. It feeds crucial insights to the other components, especially the cognitive parts. Without MDM, the brain would be flying blind.
Makes sense. And that brain also needs to know about the network, right? So network management and adaptation, NetMA.
Yep, NetMA. This provides the network smarts and ensures secure connections. It has a subcomponent that actively probes the network using tools like netperf, iperf, ping.
To measure what?
To get those real-time underlay network metrics we talked about, bandwidth, latency, packet loss, and again, critically, link energy consumption.
And it shares this info.
Yeah, it exposes this network state information, often using protocols like ALTO, so that the scheduler can make informed decisions, and it can also help adapt the network itself if needed.
Okay, so we have configuration, data context, network awareness. Now for the really complex part, putting it all together, the cognitive heart.
Exactly. This is the privacy-preserving decentralized learning and context awareness component, or PDLC. Quite a mouthful.
Huh. Yeah. So what does this cognitive heart actually do?
It synthesizes everything, the data context from MDM, the compute status, the network metrics from NetMA to basically figure out the best places to run things.
Ow.
Well, it has 2 main parts. One part, PDLCCA, creates these aggregate cost scores for nodes and clusters.
Cost scores.
Yeah. So if you, the developer, specified greenness in your CAM profile, PDLCCA calculates a score for each potential location, reflecting how costly it would be in terms of energy to run your workload there. It quantifies how well each spot meets your goals.
Okay, so it scores the options based on my priorities. What's the other part?
The other part, PDLCDL, uses some pretty advanced AI, specifically multi-agent reinforcement learning, MRL, and graph neural networks, GNNs.
Wow, okay. For what?
For forecasting future resource needs and generating those really intelligent placement recommendations. But the truly cutting-edge part here is how it learns across different clusters, especially regarding privacy.
Ah, yes, the privacy aspect.
Right.
That sounds critical if you have clusters in different organizations or regions. How does it learn without sharing sensitive local data?
It uses decentralized federated GNNs. This is a key innovation.
How does that work?
When the learning agents on different managed clusters need to collaborate, they don't send raw data to each other. Never. Instead, they only exchange encrypted model parameters, basically, the mathematical weights learned locally with their neighbors in the neighborhood.
So the learning happens locally and only the encrypted math gets shared and aggregated.
Exactly. Data stays put, privacy is preserved, but you still get the benefit of collective intelligence across the Federation. It's pretty neat.
That is neat. Okay, so PDLC figures out the best privacy-preserving recommendations. We need one more piece to actually make it happen, right? The scheduler.
Right. The final piece is the Scheduling and Workload Migration Component, SWM. This takes the recommendations from PDLC and actually places the workloads, and importantly, it handles dynamic rescheduling, which often means migration.
Migration meaning actually moving a running workload.
Yes, moving it, not just making a copy. That's vital for mobile edge scenarios. But the other big innovation here is how SWM decides on the initial placement.
How does it differ from, say, a standard Kubernetes scheduler?
Traditional schedulers often do a kind of filtering and scoring, find me a node that fits. SWM uses a much more sophisticated graph-based optimization approach
Graph-based optimization, why is that better?
because it's looking for the optimal placement across the entire neighborhood, considering all the complex DCN requirements from the CAM simultaneously. It's not just finding a good enough fit. It's mathematically calculating the best overall solution across potentially multiple clusters.
Okay, that sounds powerful. Let's walk through an example workflow. Say I'm a developer, I submit my CAM for an app with two microservices, A1 and A2. I need A1 maybe on Managed Cluster 1 and A2 on Managed Cluster 2. What happens?
Okay, so first step, you submit your CAM with your requirements, QS, resilience, whatever. The ACM component picks that up and figures out the relevant neighborhood.
Limits the search space. Got it.
Then PDLC, the cognitive heart, starts gathering all the latest data network status from NetMA, compute metrics, data context from MDM for all the potential nodes within that neighborhood.
Okay.
It computes those context-aware cost scores we talked about for every eligible node and cluster based on your CAM priorities.
So it generates a ranked list of the best, cheapest, greenest, whatever S places.
Exactly. It produces these scheduling recommendations, essentially node costs, and hands them off to the scheduler, SWM.
And SWM does its graph magic.
Right. SWM runs its graph optimization algorithm to find the absolute best placement for both A1 and A2, potentially on different clusters, that satisfies all the CAM constraints. Then finally, NetMA steps in to set up the necessary secure network connection, the overlay, between A1 on MC1 and A2 on MC2.
That multi-cluster placement. What if my CAM has a strict latency requirement between A1 and A2? How does it handle that link across clusters?
That's a key part of the scheduler's job. It guarantees those channel requirements. SWM doesn't just place A1 and A2 and hope the network is fast enough.
It calculates it.
Yes. It ensures the total end-to-end latency meets the requirement. It calculates it like the latency inside cluster A, where A1 runs, plus the latency of the network link between the clusters, plus the latency inside cluster B, where A2 runs. That total sum has to be less than or equal to what you asked for in the CAM.
Okay, that's robust. And you mentioned migration, since conditions change constantly in the edge cloud world.
Correct. The whole system supports proactive rescheduling. If conditions change, maybe network quality degrades, or a greener node becomes available, the system can decide to migrate a workload.
Actually move it while it's running.
Yes, that focus on migration, not just replicating or restarting, is really important for these dynamic environments where resources might appear or disappear.
Wow. Okay, so this CodeEco framework, it really does seem like a major step forward. It takes this incredibly complex CEI landscape and tries to make it, well, manageable and optimized.
I think that's the goal, yeah.
Yeah.
It provides a foundation for orchestrating applications in a way that's decentralized, cognitive, resilient, and ultimately puts the application's needs first, not just the infrastructure's limitations.
It really shifts the focus. Which brings us to our final thought for you, our listener, to ponder.
Oh, yeah.
We mentioned that the AI component, the multi-agent reinforcement learning part in PDLC, uses an auction-based algorithm for placement.
Right, for deciding which agent gets to allocate a new pod.
Exactly. So when a new workload arrives, the different agents representing different clusters or resources calculate a Q value, basically, the expected value or reward of taking on that workload. They then broadcast this value to their neighbors.
And the agent with the highest Q value wins the auction, gets to place the pod. A kind of competitive negotiation.
Right. So think about that. Scheduling resources, which used to be maybe a more passive matching process, becomes an active, almost economic negotiation between these AI agents. How might this mechanism, this constant calculation of value and expected return for hosted workloads, how might that change the future economics of how we share and allocate resources in these big multi-tenant infrastructures? Does it turn resource allocation into a kind of continuous, dynamic, privacy-preserving marketplace run by AI?
That's a really interesting question. Where AI meets economics meets infrastructure, definitely something to chew on.
Indeed. We'll leave you with that thought. Catch you next time on The Deep Dive.